No questions? Okay, so if there are no questions, then we will start right away. So as you might remember from the last lecture, we have been talking a lot about containers and similar structures. So I was thinking a good subject for today's lecture would be to write our own more sophisticated container. So as you might remember, in the past we have written a very simple linked list, but now we can try our skills at something more advanced. That would be a hash table. So we will create a new project. Zack. And we will, so unlike the simple list which we created using C++ directly, we will first start our hash table maybe just using plain C, and then if we have enough time we will look how we can port that to C++. So we have asked our starting project. Let's add a couple new files. Hash table C and hash table H. We should rename our entry file to main to not have object name conflicts with our hash table table. Hash table H. And for this approach, we will really do everything in the C way of things. So we will not use pragma once, but the preprocessor if and def. If not define hash table H, then define hash table H and ndif. So this ensures our approach of ensuring a single include will be C compatible. Here we of course include our hash table. Let's take care for the capitalization, hash table H, and we will also include, do I have a typo? Hash? Oh yes, I have. And here we will include oops, std, no sorry, std lib H. That should be enough what we will need. So what we will need for our hash table before everything, of course, will be a structure to represent the root of our hash table, so to say. So let's call it as my table, and we can also use the C approach of defining struct. So type def my table, type def underscore my table as my table, type def struct as my table, and here we can add some members. So first I think we will require will be some pointer that will point to our actual table, as the name hash table well suggests. So let's call it my entry asterisk buckets. We will of course need then the next element, sorry, the next object, which will be representing a single entry in our hash table. So we call it my entry, and here I call the variable buckets because that's the standardized nomenclature to describe the list, the array which will be holding all the entries in our hash table. So our entry will of course need an integer value and hold the hash value itself. Then we will need to have a pointer which will point to our data, whatever our data might be. And what we also need is we will need a pointer to the next entry So every entry in our hash table, so every bucket, so to say, will contain a linked list, one unidirectionally linked list of entries which fit into the same bucket. And what we also will need to ensure that we can uniquely retrieve elements, since as we mentioned earlier, the hash function that generates our hash values from the key might not necessarily be might not necessarily yield a unique hash value, either because it is not well working, or whether given that our data might be in some way degenerate such that they will yield similar results, or even in the simplest case where we really have just much longer data than the hash value itself, so it isn't unavoidable that there will be different inputs generating the same output at some point. So what we will want to do is we want to also have a copy of our key. So here we will use a nice trick. We will create a char array key of size 0 and the idea is when we then allocate our entry structure, we'll just add the amount of bytes which we need in addition to fit the key into the same memory block, and then we can access this additional bytes which follow directly our my entry object using this key member of the object. This is a very convenient way of saving on memory allocations and making the memory management simpler by just having a bigger structure. And instead of specifying a fixed size which would limit us, here we can really then dynamically, once we are using and allocating this structure, specify the size which we will want to use. Another variable which would be useful to have will be a size size which will tell us how large the data object is, although that of course depends on how we want this hash table to operate in practice. So there are two ways how this can operate. One would be where we are storing the actual data within the array, and another one would be where we only store pointers to the data and manage the data separately. The size variable is not necessary, but useful to have. And what also would be good to have will be a variable that will hold the size of the key in case we want to do some in case we have a key which is not, for example, null terminate. So if we would use a char like this, the expectation, for example, might be that we want to always use a string as a key, but obviously that might not be the case. So we will design our hash table such that we can make it hold any sort of data. So therefore we'll also add a second size parameter for the k. We'll just call it key size. Maybe we should call this data size so that it is clear, and just for niceness, let's maybe move the next entry more to the top. The important thing to note is that if we use this trick to keep the key inside the same memory block as our entry, that this must be the last member in our object. It cannot be followed by anything else, otherwise accessing it will of course overwrite that member. Okay, so we have here our buckets. Then a few other things that will be useful to have will be the size of this, sorry, and this needs to be a double pointer, because this will basically be an array of pointers to such objects. So we need to make like an array of pointers or a double pointer. And as I mentioned, what would be nice to have would be some sort of counter that will tell us how many buckets we have. Call it bucket typos everywhere, bucket count. And another very useful variable to have would be to have element count or entry count, so that we can quickly check if there is anything in our hash table or not, and if there is, how many entries there are. Depending on how we are using the whole thing, we could of course opt for storing So if we always would have the same key size, then we could opt for storing the key size in the table and then specifying when we create the table which key size we want to use. But since here we are rather focusing on keeping the implementation more generic, we will not use such optimizations for now. So we have our hash table. Then we will of course need some function which initializes it. So void int init my table, and this thing will of course need a pointer to our table itself. And since we are not storing any other data, it will not need anything else. So let's start with implementing it. This can be in fact quite a simple function. We just name set our table with zeros, and we take the count of bytes that represents the size of a table. So let's now go to our main function, include our table, create an object of type table. We create this on the stack for the test case, then we can init our my table, provide a pointer, so this will do the initialization. Okay, and then let's proceed to the next function, which we'll logically need. So obviously the next useful function would be a function to add something to our table. So add my entry. Maybe it's boring to always have name. Just let's call it gosh. And to my table. Let's go with this name nomenclature. So since we are using C and not C++, we cannot define any functions on the table itself, so we need to define individual functions individually, and those functions will always take the table as the first argument. If we have time and we later would convert our table from C to C++, then we would of course omit the argument and make the functions all live on the table object itself. Now the other arguments which we will require here will be the key itself. So const char stern key, size of the key, and then we will of course require the data. Key size and data size, and that's it. So one thing which we haven't now thought about is how we handle the situation when there already is an entry in the table. So one strategy would be to just overwrite it, and the other strategy would be to return an error. For now, let's just go with the overwriting approach. That seems to be easier, and if we have time, then we can later extend this function, add to it a return value, which will return an error if the element already exists. We could also use an additional argument which specifies whether the function is allowed to replace an existing element or not, etc. So since it's our own container object, we can use it as flexibly as we want. So let's now use it and add something. So again, we need my table. Let's do the adding in the loop so that we can add multiple elements. So for for simplicity, let's add string std key is equals let's call it actually key underscore plus std to string I, and so we will have our key here, c string, and size will be key punct size. At this point we could of course decide to make size +1 so that our key actually includes a terminating 0, and I think this would be nice, so let's do it. And now we have to provide some data to be stored. So it pretty much for our test case does not really matter, but we could, for example, store the integer value here. So what we do is we make a reference on I, and as a data size we specify size of either I or int. Both are valid, both would work. Okay, so now let's implement the body of the function. So one thing we can do outright is we can create a new element of our entry type. A optimization maybe for later could be to only create element once we decide that we need to replace it, and once we decide that we need to add it, and if we see that we only are replacing one, then we could reuse the existing element, just change the data pointer it is pointing to, since the key in this case will be the exact same, so the amount of allocated memory for the key will be enough. But that's an optimization we can do later. So my entry is gleich and here size of this plus key size. What we will also need to do later will be allocate some memory for the data. And what we can actually do here to save on allocations is we can use the existing the one block to allocate also a data pointer. Actually might look nicer if we define it like this. The idea is that just the data here will be just be pointing behind key, but since key can have a different size, so we actually need this pointer explicitly here. The key which is provided here, the key member, since it's an array of size 0, unlike the actual pointer, will not take any memory. Just accessing key will tell the compiler to access the memory after key size. So this is really an extremely efficient approach, while this approach here with data is the next best thing. So if we would have like multiple members in our structure, then of different size, of course, then a reasonable approach would be, for example, to allocate one memory block and then have multiple pointers in our structure pointing to the different explicitly sized elements. And of course, when we know that some elements will more or less always have the same size, then it's easier to have an actual array inside our structure. There are some considerations, of course, to be taken generally when handling and creating structures, namely that a structure which has a pointer like this is not directly serializable, so you cannot just write it to a file and in another program load it from file, since then of course the pointer will no longer be valid. So while a structure which would only contain arrays of fixed sizes would be really nicely portable, you can just write it to file, load it from file. As long as it doesn't have any pointers, it will work. The typical approach here is, if you need an array of varying size, then to write some manual serialization function which will write your structure to file, and here replace, for example, the pointers by an offset value. It is encountered often in the Windows API that the structures returned by it will not contain pointers, but actually will contain offset values, which makes sense from a bug avoidance standpoint, but of course makes accessing those variables a bit more convoluted, since you then need to do arrays pointer arithmetic to access the right offset. Since here for our use case we are more designing a data structure which will hold data in memory and is not expected to be serialized to disk, then we will here simply go with this approach and not put any more thought into making this portable. Okay, so we have created our memory block which will hold our entry structure, our key in its entirety, as well as the data, although the data is super small in this case. then it is expedient to just memset everything to 0. Although, of course, if we would be focused on maximal efficiency, what we would do is we would, for example, only memset the first portion of the structure. So, for example, only memset size of entry without memsetting key. Actually, we can do it this way. Sorry, copy and paste error. This way, we have nicely resetted the structure itself, but the key and the data will be containing garbage, or in this case, since it's a debug build, it will contain the what was it? I think CCCC value indicating that it was not initialized yet. Okay, and then let's start filling the structure up. So first of all, we have the hash value, which we will take, on which we'll work in a second. Then we of course have our key size, which is just key size. So we will fill this, and the data size will be data. Then we will need of course to copy key and copy data, which we'll do in a second. But first we'll focus on our hash value. So we will need a function which is not yet exposed to the outside world, which will be only exist in this file, which will calculate a hash value from a input. We will optimize this function to work with strings, and one of the improvements which we can add later on, if we have enough time, will be to, instead of using a function which is just the same for all the instances of our table, we can actually make a function pointer on our M table, which then the user will have the option to point to a custom hash function. This is very common when implementing hash tables, that you provide your user with the option to provide their own hash function, since you want to have a well spread hash values, and the user knows best which type of keys they will be using. So in this case, it is prudent to give that option to the user of your code. When taking a look on STL implementations or the Qt implementation, a custom hash function is one of the first things you will notice, as the template arguments which are available when you are instantiating those objects. So in our case, we went for using an integer value. Actually, maybe we should use unsigned integer, but it doesn't matter. Let's stick to integer, and let's implement our function, my hash calc. Oops, need to see. And this just takes the key and the key size and generates a hash value. So let's give the hash value some initial value. Generally, when trying to hash something, it is a good idea to not like start from 0, because usually the data you are putting in are either structured or might start at 0 themselves. So it is a good idea to just start at some nicely random start value. And then let's just loop through our key. So for size ti is equals key size is equals 0, and I is less than key size slash I plus plus. And here we will then add to our hash modify our hash value. So basically, this value will return at the end, and we are just now putting it through the meat grinder, so to say. So one important thing is to, of course, always keep some portion of your existing value. So in this case, we are, and what also we want to do is, since we are entering values which only have 8 bits and our hash value is 32-bit, we want a mechanism that will kind of blow up the value as we are putting in a new data, and kind of apply the data to the whole value range. So what we are doing here, for each iteration, we are taking the old value, shifting it by 5 bytes to the left, and then to make it a bit more complicated, we then add again the existing value, which we already had before, and then to add the value which we are actually processing, we will XOR this thing with our key at the position of I. Zack. Oops, small typo here, and then we can return our hash, a value. Yeah. So we have our hash function, which we now can use here. Hash function again, we provide the key and the key size. Here we said we want to copy, so just entry key, comma, key, comma, key size. And then the same thing. Not the same thing. And now we need to calculate the offset where we are allowed to write our data. So char asterisk data. Oops. Data ptr is equals. We could either do it the full way or just do it the quick way. So what we are doing here, we just will add the key size to key, and this will directly give us the right pointer for the first memory byte, which is located after our key in our data block. And then we just use memcopy. We can improve that even more. We don't need a temporary variable since we have our data pointer. We can calculate it directly here, and then we can just use it. So here data and data size. Okay, so at this point we have created our new element, which we'll be inserting hopefully into our table. Maybe for simplicity we will actually modify the behavior to only be able to insert if there is no value with this key. So we will, if we encounter an entry, we'll just bail out and dispose of our element and return false. Right, one more thing to keep in mind, the bool keyword is actually not available in C. It just starts with C++. So we have two options. We can either use the uppercase bool version, which, well, if we would include Windows H, but we don't want to include Windows 8, so we will just use an integer as our return value. The boolean as defined by the Windows header, so the capital letter bool, will just use a unsigned byte, so an unsigned char as a type to store our result. But it is very often seen in C that you just use an int no matter what you are returning. Also to note is that there is no lowercase true or false in just plain C, but again the Windows H header provides you a true and false written in capital letters, which just evaluates to 0 and 1 as a preprocessor definition. Okay, so we have created our object, we have changed our mind on the prototype of our function, of our add function. So now what we will want to do is we need to find out whether we need to resize our bucket array. So since initially it will be 0, then we will have to, but let's make a function here to do that. So if mtable, what was it, enum count. And one thing we can do to optimize the memory use is we could define a variable which defines how much we want to reduce the amount of buckets used in comparison to elements in the array. So the way a idealized hash table would operate is that it would have exactly one bucket per entry. But since this can be somewhat inefficient with regard to memory reallocations and the fact that in real life conditions we will have some amount of hash collision, so keys resulting in the same value, it is a nice idea to have here a value that allows us to define a certain kind of reduction value for the amount of buckets which we want to use. So let's define a const int reduce buckets. We will start with 0, but we can then change this to 1 or 2. So in our check whether we need more buckets, we will use the bit shift operator to implement basically a division. So we either not divide. So if it's 0, then we don't divide at all. If it's 1, then we divide by 2, and if it's 2, then we divide by 4. That's a nice thing about this trick. You cannot divide by 0 and get a invalid and get an infinity. Okay, and for the table now we just compare this with the bucket count, and if we need, so if the value is like greater or equal, then it means that we need to allocate a new array with some buckets. And you will notice that since it's an equal operation, if all the values are zeros, so we start out with an empty table, this will also evaluate to true. So now we want to compute the amount of buckets which we want to have. So int bucket count. We could call it new bucket count, but oops. And then we just go with the current bucket count. And if this is greater 0, then we will just double our bucket count. So here shifting into the left direction means a multiplication by 2. The reason here is we don't want our table to just need a reallocation each time we add one element. We want to kind of go in jumps, and doubling it each time we reach the limit is a good approach. And of course, if the value was 0, so then we just need to specify that we start out with 1. We could in fact specify that we want to start with some start value. We could for example say that we want to always start with at least 8 buckets, which actually is a good idea, so let's do that. This will ensure that if we add a few elements, 8 is not too much and not too little, it's just like the ideal value, hopefully. So we will do that. And then of course next steps will be 16 and so on, since we are always doubling. And here now we will invoke an yet non-existing function, size my table, and we will just pass to it our table and the new size which we want the table to have. And our next step will be to implement this resize function. So let's do that. Let's do it here, since we might want to keep this function close. We don't really need a return value, since here we will be not taking care of memory allocation errors. So if you would want to use this code in production, we should add a throw if this fails, or we could add everywhere a function. Actually, maybe that's a good practice. Let's do that. So if entry, if no entry, then return. Yeah, if we would want like a easy check, then we would just always return a 0 on an error. But since we might have different errors and we would want to communicate them, we can define our function such that returning 0 actually means success, and returning something non-zero means a failure, and what we return will denote which sort of failure we have encountered. So for simplicity, let's just say -1 is memory, out of memory. And another thing to note at this point is that there is also a concept, not concept, how to call it, standard, let's say it's the standard, that returning values below 0 means, of course, failure, but returning 0 means success, but returning something greater than 0 means success but. So like it worked, and then you might want to get some additional information. So one option would be, for example, if you are enumerating something and you got results, but you passed an array which was not large enough to take all the results, then one of the positive return values would be that there are more results. Or if we later allow the function to override entries, then we could say that returning, for example, +2 would indicate value was inserted, but an existing value has been disposed of, or something like that. So here we will stick to using negative values for now, and of course a return 0 on success. And that therefore we will here also have a return value, and another thing we will want to do is we will want to then now of course evaluate the return value which we got here. So we have a table, and we need to assign the return value to a variable, and if this is less than 0, then we return the return value. If it was larger than 0, then it was a error which, well, it was something, but it's something that we can run past. It's not something that breaks forever. And actually it would be a good strategy to keep the value, let's say here, so we start with 0, and if something happened in our resize table, then it will be passed to the next function, so that it can be inspected in case we want to do it. Yeah, and of course here, since we haven't had the opportunity to get any value, we just return -1. Okay, so now let's implement our hash function. So one thing to keep in mind is that when resizing a table, this is not super easy, and especially in our particular case where we have this hash table which uses hash values, and as you will later see, as the table grows, the used portion of the hash value changes. It will really kind of need to rebuild the whole table from scratch, which is why it is a good idea, as we have done here, to already start with a table of at least some size, such that we can really reduce the amount of these rebuilds. So what we will be doing here is we'll just convert the whole table to a list, if there are any, which we'll check in the next line. So one thing to keep in mind is that if we would fail here at some later stage, then it's kind of an irrecoverable error, because our kind of new table already was, the old table was already kind of messed up, and it can not easily be restored. So maybe actually it would be a good idea to allocate the new table right here. That's the name. And because this way, since we allocate it first, we can in fact bail out and just return a memory error. And we need size of for each turn. So we just take the average size of a pointer. We could also write size of my entry 1 asterisk. Everything evaluates to the same size. A pointer is a pointer is a pointer. But we need to multiply this by the amount of buckets which we want to have in our table. And here, if this does not exist, we just return -1. That said, conceptually this is the only error which we might expect to encounter here. 0. And actually a thing to keep in mind is that even if we fail to allocate the table, we kind of still could proceed by the insertion process with the old table. We would just not be able to make a bigger table, but theoretically we could. So we would have the option to decide that we actually want to continue. But let's for now just bail on every error, since a low memory condition generally is not good anyways. So it's probably a safe bet to abort our application when this such a condition occurs. Okay, so here I said we want to check whether we actually have something in our table, because if we don't, then we can just make a bigger one, which actually will be the case when we enter for the first call. We will resize, but we will not have anything to resize from. Okay, so right here, so we have here our table. Now we make a small loop for it's like table bucket count, and here I minus, so we will define our loop slightly different than usual, just to mix things up. So instead of like having initialized it with a value and then comparing against something, we just initialize it with 0 and comparing against a value. What we do is we initialize it with the count, and then we just decrement and check in the same go through. It's a nice small change. So here what we need is we need to take the entry from this bucket, the first entry from this bucket, that is table buckets from I, and now we will check if there is anything in the bucket, and we will pull the things out of the bucket. So entry ungleich not equals, I mean null, and here we will need a pointer to the next entry, since we will be doing something to this entry. So next entry, this equals entry next. Now where's our entry? Entry next will be our entries array from before. Then our entries will become our entry, and then of course for the next loop our entry will become next. Zack. So once we are done with this loop, all the entries from all the buckets will be part of one singly linked list, called into a pointed to by our entries pointer. So the next thing we do is we free our existing bucket array, and now we have already allocated our buckets. We actually could then here maybe memset it to keep related code together. Memset of course with the needed size. Zack. But now here, since we are actually starting using it, we will rewrite, so to say, our table. So table buckets is equals our buckets. Zack. Table bucket count will be our new bucket count. Yep. And now the last thing left is, in case we had some entries, we will need to re-add all of them to our hash table. So actually we can copy and paste quite a few things from here. Oops. This one of course changes, because here now we go for entries, and here inside we don't do this. We just need the next value so that we can later go to it. And now what we'll do is we'll invoke a function which will actually add an entry to our table. So as you see, for now we are kind of going further and further down the rabbit hole from our initial add to my table. So the next function we need will be a void. It should not fail. And we call it insert to insert to table, insert to my table. No, that's not a good name. We want some indication that it's an internal function. Let's call it insert. Let's call it insert my entry. So insert my entry will take, again, as everything takes, a pointer to our table. Although we could actually just pass it the buckets variable and then add some more logic outside, but let's stick with that. Then it of course wants the entry to be entered. Zack. So insert my entry. So here and we wanted the table right here. So here we are. and now we need to calculate the actual index value for the bucket where we want to insert it. So we will be going even further down the rabbit hole. Team is equals get my bucket, which takes again table. Every function takes table because we might want to put some useful things on the table later. And now we can, since we already have the hashes calculated, just use the hash value here. Okay, and now we find the right entry. So table buckets at index. So what we wanted to have a pointer on the right entry such that we can actually edit the value inside our bucket. So we here kind of reference it by index, and then we take a reference on that. Alternatively, we could have written table bucket plus index. That's equivalent. Maybe let's stick with this since it's more direct. They do the exact same thing. So we have our entry, and for simplicity we always add at the top of our list. So not like add to append to end, but we just insert always to the beginning. That's why the function is called insert, not append. Yeah, and that's it. So we have here our entry. Next, we'll be pointing to the thing that was before in our table, and now we will overwrite the value in our table with the new entry value. So as we have noticed here, we are still missing one function. So this one is size team, get my bucket, table, comma, int hash. Okie dokie. And this one is quite trivial, although it, well, trivial. It's quite interesting. Let's see what it does. We want to just return the hash value, and now we want to end this with table bucket count -1. Any ideas why? And any ideas why this works? Well, what we want to do kind of is we want to map a value which can be from minus to plus 2 billion onto a value from a fixed value range. And normally when we would want to do that, so the always working way would be return hash modulo bucket count. So we just take the modulo operator, but since this basically is division, it is slow. On some hardware it might not matter, on some hardware it might be just as fast, but it will still consume more electricity. So if we want to be super efficient with everything we do, the best approach would be to somehow use the logical operators to get to the same result. And we can do that, in fact, here using this trick. Although this trick works solely under the assumption that the bucket count itself is a multiple of 2. If it's not, then this doesn't hold true, and it would fail. So let's quickly go through a couple examples. So of course one option would be we have 1 in our array. So 1 minus 1 gives us 0. Obviously, that's boring. Okay, in the next option, let's say we have 16. So decimal 10. 8 would be just 1x8, obviously. So we start with 16 here for test. We remove 1 from it, and what this basically does is it does this. Maybe I should write it like like this. What it does basically is it decrements it turns all the zeros which came before into ones in binary, that is, and then it removes the first one from the thing. So this is kind of the result which we get. Of course, providing preceding zeros is kind of unnecessary, so let's not do that. And now let's write down a few more examples. So okay, so we would have F, FF, 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 oh wait, sorry, FF, FFF. Yep. Wait. So this we broke one. That is not correct. One more F. Now it's correct. So basically, if we have values which are just a power of 2 and we remove 1, we just remove the 1 and replace the zeros with an FF. And then, since we are using here the AND operator, it will just mask all the other bits, and we will only use the lower portion of our hash value. And in this way, we can efficiently arrive at the same operation as this one, but under this necessary assumption that it is always a multiple of 2. So here it means that, where are we? Here, we should add a comment that bucket count and it kind of is, since we are just shifting in. Well, we could start at the 1, but if we start at an 8 bitwise, it's still just a 1 at the right position and no other values. And we add this here to the comment, comma c get my bucket. Okay, so we have our get my bucket function, which we use here. We got the bucket, we have filled in the list, the insert is complete. So we can continue implementing our to my table function. So let's proceed with this. And the nice thing is that we kind of already have almost everything we need to proceed. We just use here our insert function. We pass to it now again the table, and we can pass to it our entry which we have created. So in this particular implementation, we are not even checking whether this entry already existed. We are always adding it even if it existed. So we can, in this case, hold multiple, for now at least multiple entries with the same value. Sorry, with the same key. Multiple entries with the same key. And later we will improve on that. So the last thing to do is we need table entry count plus plus. Indicate that we have one more entry in our table. Okay, so since we are now already at the, well, in some way minimal functioning stage, let's run it, and then let's put a breakpoint here on the return statement, and then we will see whether our table contains what we expect it to contain. So it should have something failed, so it should have 8 buckets, and it should hopefully have somewhat equidistantly spread values. Okay, one more bug. I don't like this. Okay. C is quite a bit more. Okay, we have a new bug which we have int my table. Yes, we forgot one thing, namely that the decoration for a header for C is different than for C++. So so what we can do is we can put the whole thing here into a extern C, but this again adds a catch-22. We don't have like extern in plain C. So what we do is if def f underscore C++, then we can do extern C see. So the idea is that when the header is included by the C file, it will look differently than when it gets included by the CPP file. And here we have just the closing brackets, and we don't want that. So for the C file, those kind of don't exist, they won't be invoked, but for the CPP file they will be, and then the prototype decoration for our functions here should be correct. So let's run, and it's thinking, voila. But we managed to crash something. So let's see what we have done wrong. Entry. Well, that thing contains garbage. So let's buckets. Looks fine on the first glance. Bucket count. We haven't changed bucket count yet, so that should be fine. Buckets I. Let's put a breakpoint here and see what's wrong. Okay, so we have our first entry, which has some hash, which has some data, which has some key. The next thing, okay, the next entry doesn't look validated. We forgot to set it, so we memsetted the entry here correctly. Somewhere we forgot to clear an entry. So we insert pointer next. The insert must be somewhat not correct. Next is pointer is entry. That looks fine. Here we get buckets plus index. That looks also fine. Let's step through the. So let's first reduce this to 1 so that we can catch it at the earliest opportunity. We'll later increase it again to a larger value. So we have here our first go through. So we index. So first, right, where did we put the breakpoint? Let's rerun that. We don't want this breakpoint. We want to start. Let's say we start here. Okay, so first of all we enter this function, we get 1, rightio, we enter, we allocate, we memset the right amount of yeah, that should be fine. So this will be of course null, so we continue to the next, we assign the new element, we set the new size. And now we didn't have anything to do here, so we continue. Zack. And now we do the inserting. So we take an index 0, obviously, since we only have one bucket. Get a pointer on our bucket. So here we have something that points to, well, null. We say that the next of our entry will be null, and then we set our bucket to our entry. So now if we take a look at our table, the first entry, it contains our value, and next, wait, okay, next is wrong. What did we break here? We need the value from here. We forgot an asterisk. Now it should work fine. So let's ignore this. Zack. It worked without a flaw, so now again we should have about 8. No, actually now we should have 16, since we have 10 elements and we have no reduction factor yet. We should have the next figure bucket count. Again, here as you see we have 16 buckets, even though we have only 10 elements. And unfortunately here we cannot nicely view any one past the first one. This is somewhat not cool, but we can assume that it's fine, or can we somehow improve that? Not really, the intelligence is not very smart. We can inspect those things like one by one. But for now, let's say it's okay. Can we somehow? Sure, we can. We can create a vector and then help ourselves to some more meaningful debug information. So yesterday, small v vector. We need the right type here. Entry vector test. Reserve. Table.bucket count for pushback table bucket count punkt bucket count table punkt buckets at e. Why doesn't this like it? Because that is a pointer. And might not be the most elegant thing, but at least it allows us to easily inspect our table. So as you see, we have some entries here, then we have a couple empty entries here, and then we have entries there. And it kind of looks like all the next pointers would actually be zeros. So our hash function worked exceptionally well. So now what we can do is we can slightly improve on that. So let's say we want a reduction factor of 2, and then here we start with 8. So ideally we would only allocate one bucket with 8, one bucket table with 8 entries. That didn't work at all. Why did I? Of course it did. I changed the wrong value. Yep. Okay, so we have our buckets. We have only 8 buckets, and some of the buckets will have 2 values. So this one doesn't. This one doesn't either. This one doesn't either. No, neither this. No that. No that. No that. This one does. And probably the first one also does. And they don't have any further. So obviously using something that's just a integer that grows is kind of the easiest case for most hash functions. So what we could do is we could just feed a random value to our key, and then we will store the index as the value. So now we should get some more interesting table. So as you see here, for one of the buckets we have 0 hits. For another one, okay, we have 0 here. We have 1 no next. Here we have 1 next, which has another next, which doesn't have any next. So we should have, I think, one more with a next. This one, and it has no more next. So as you see, this works quite nicely. So our hash table is already functioning. So the next thing which we will want from it is, of course, some ability to retrieve values by key. Since we here entered a random key, it kind of would be difficult to retrieve something, since we don't know what keys they are. So we will here go just again with the I for later use, and well, that's that. So let's now add a find function. Int find in my table. We'll copy the prototype and here just change it very slightly. So let's first copy the function here, and then before we implement it, we will take a look on how the function will be supposed to work. So we will have again a loop 0 from 10. We will generate our keys, the same keys, We could keep it rand and then just push the keys to some vector which will key reuse, so we can do that later on. And what we will need is we will need some size t variable which will receive our data size, and of course a well, since it was an int, so let's go with int asterisk data. Okay, and now we'll be using our find function. Okay, so first of all we need to have a reference on table, not just table. Then for the key we use the same code as here. And now for the data we make a reference on data, but this will not necessarily work. We need to change it to a void asterisk asterisk, since otherwise it would not be compatible. And here for the size we can just go with reference on our size, and we will want to know whether we were successful. So if this is greater or equal 0, then we can, let's say, int f found value percent I at key percent s backslash n comma asterisk data comma key c string. And if it fails, then it will return, let's say, -2 or some other value. Actually, another good practice is to define your error code. So let's do that. My table error out of memory is -1, and not found will be 2. I mean -2, of course. We could, for completeness, define my table error success or error none. So it's not an error, it's fine, which is 0. And well, let's just call it my error success. There are different approaches to the naming convention, so you can either like have an error none or have a success, an explicit one. If you don't intend to use other success values, so just you have 0 and negative values, then error none is a good approach. If you want to have success values, then it is recommended to have like success, and we would have success underscore more results, or just table underscore more results. We will see what we will want to do with that. But for now we have this. So here we just care for success and we don't do anything else. We could of course also define actually a checker. So if hash define my table is success x, and just have here x is greater equal success. So here, instead of if and an explicit value, we could do it like that, which is quite nice, and it avoids having the risk of making a is equal 0 check and then bypass some successful values. Successful results. So let's start with our find function. One shortcut we can take is that we can check that if there are no buckets in the table, then we will just return instantly. If exclamation mark buckets, then just return error not found. Because if it's empty, then it's empty. So that it, and usually if you can have a quick shortcut, then it's a good thing to have it. So now next thing, we want to get our hash for the key. So we have our hash function here already ready to be used. Then we will also want to get the index. We had a function for this as well here, which is almost right. We just need to skip this. And now we can directly try to look if we have this actual entry. So as said, the hash values are not unique, so we need to search through some of them. You can, for quickness, copy again some code. Actually we need much less, so here we go with table, table buckets from index, so we pick the right bucket instantly. And since we are not modifying anything, it's a rather simple loop. We could of course here use a for loop, but let's stick to the same type of loop. It looks nicer, in my opinion. So now the only thing left is to check whether the key is actually the right key. So if key, actually first we could check key size, because the length may be different. So if key size is right, only then we will do the next check. So already here we can save somewhat on our computation, because we can use a shortcut. Why is it complaining? Entry keys. There is no typo. Should be fine. It probably is just complaining because we're not yet done. So now, since we know that the keys are identical, we can use memory compare for the entry key and key size. If the size would be different, we couldn't use compare. And as said, if it matches, it returns 0, otherwise it will return plus or minus 1. Okay, and so if we have a success, then now we will that one my table success. And the important thing, we need to set our return variables. So asterisk data is entry data, and date asterisk data size is equals entry data size. And of course, if we have looped through all the entries in the bucket, we will here just return not found. So let's try this. Actually, we already have the try case, so we can run it. Now, one thing to keep in mind is that the behavior here is slightly different, since here we are kind of making a copy, while here we just are returning a internal pointer. So depending on your use case, you might want to adapt this behavior, for example, such that, for example, one option would be that you need to pass here a pointer which then will be owned by the table on success, and then we don't need to allocate the data explicitly again inside this. So in certain use cases that would be an optimization, but the implementation which we have chosen here is designed to be most reliable. So this is a good approach, even though it in some cases does a few things a few times. So if we would have a complex structure, then we would need to allocate it here, and then we would have making a copy of it. Also, one thing to keep in mind is that the way this works, since it is making actually a full copy, it would not properly handle a situation where you would have a more complex object. So we can only use simple C structures, and we need to keep in mind that if it's copied, it will not be a deep copy but a shallow copy. So if our structure would have pointers to other pointers, then basically after doing the add, we would know that we have to dispose of the structure we added, but not dispose of the things the structure is pointing to. Okay, so let's run it. Suck. Well, we didn't crash, that's already good, and we have found that's not quite right. We went through all the keys, but we didn't get Sometimes we just got 0. That's not what we expect to happen. So we have to debug why is this happening. So we have data, it's an integer. We take a pointer on this. Here we assign it just the internal pointer. That theoretically should be right, but apparently it isn't. Copy data, so we copy this here correctly as well. What is wrong with that? We are not reallocating anything, so that should be right. Well, we will have to debug this. Let's quickly here put a break. Actually, we can run this as is, and then we'll just inspect our test array. So we already noticed that well, 0 actually might be right, but 4 definitely isn't. Oh, this time more of them was correct, so this is some sort of very unpredictable bug. Again here, but one pattern that emerges is that while it can fail, it will only replace the right value with a 0. It will not do any other sort of corruption. So let's see in our table. Not this one. We will need to check the key. Well, we don't see the key content, unfortunately, since we have defined it as size 0. So what we might either want to do is to add a add something that will just count. Oh wait, I think I know what the problem is. No, I don't. It should be right because we give a point and then we make a copy. So this, just check whether we are properly copying things. Data size, data copy. We are properly copying things. What we can do is we can inspect the actual data, the things pointed to by this. So we know this should be an integer. So we go to our table, with asterisk, and then okay. So the entry at 0 is valid. Does this have a next entry? This has a next entry. The data here is 0. Well, whether this one is right, we have to check. So we can take the value here, so k1, but it points to 0, so it's not correct already. So the problem is that our data object is getting sometimes corrupted. Why is that? Key data. Do we have enough size? We have size of my entry. We have key size and data size. Should be right. We can add some test code here. If and just test whether it got corrupted. If this is not 0, then we -3, and let's put a breakpoint here. So now first thing, we will test whether the corruption happens already here, and it does not. So the data seems correct, and it only corrupted once we did something else to it. So what we can do is we can increase this to 16 and then see if without any reallocations this will behave correctly. And as we see, it does not. So that's interesting. That the check was successful, but we apparently had a corruption. Did we do everything correct here. Entry from bucket, entry that is just a pointer, which is just a value, that should be fine, and not null. Entry next, return data and data. That looks right. You are not manipulating the value further down. Okay, so what we'll do now is we'll add a function to dump the entire table's content, so then we can test whether when it starts getting corrupted. So void dump my table and little t, and ideally we would want to make it such that we can print the key and the value. So we will add two function pointers. Print key, which takes key size and key as argument, and which takes, okay, so here, since these are function prototypes, we don't need to provide the names. We will do that to keep the function short. Okay. Okay, so let's start. We can go with this for to make things faster. As we said, next will be done like this, and then we can have some code here, and we just iterate through the whole thing. So let's maybe first, no, let's not do anything. Let's just invoke our print functions. I'm thinking right now that would be elegant to indicate in which bucket they are contained, and that actually would be. So let's go with that. Then here we want to indicate the bucket, so we'll change the loop here to go from 0, smaller 0, e++. Why is it complaining? Because I forgot this here. Bucket %i, comma I, sorry, %i is fine, we can also use %d, and inside here we'll be then printing all the entries. So to actually print the entries, we will use print key, entry key, and entry key size. Then we'll print just a separator. And with the next one we'll print a backslash and a print value. They call it, I call it print data. So let's go with print data. Data size. Okay, so now let's use the function. First we will validate, well, first of all we will change this here to behave the way it always behaved, and we'll here add the dump function. So we dump our table, comma, let's copy quickly the prototype. This time we will need to provide a value, so that was key, that was key size, although we don't really care for key size, since that's since we know that it is just a string. Then we'll have the other function. That looks better. Why is it? What is this complaining about? That this is not an extensi. That's annoying. So let's explicitly define those functions. I wanted to use lambda functions because that looks nicer, but in the case we implemented this here, we need this explicitly. So void print key, void print data, print key, comma, print data. So now it's not complaining anymore. And in let's do it like this. And in print key we just print f %s, comma key. We don't care for the size as mentioned. And here we know that it's an integer, so just %d, and then we cast. It should say data. Int asterisk data, and we need the value from that. Okay, so let's put a breakpoint and let's run it and inspect our table. We forgot a semicolon. Okay, so dump bucket 0 contains key 9 and key 1, which is 0. This one is broken. Key 0, 0. Key. Okay, it contains a lot of broken values. If you would run it, further we will notice that a lot of values are just zeros. So apparently the error starts already when inserting elements. We could of course print it each time after we inserted something, but that does not sound like a very good idea. So what we can do is, again, we can go for the function to see if we can spot something obviously wrong. Entry data, it looks, that should be right. Copy key is key size, and then we go for the offset of key with this, so we can put a breakpoint here to validate that. So entry key, as we know, will say key 1, it will say key 0. And data is 0, of course. And then we can check whether this, as expected, will point to nothing. We can actually go to this address in our memory overview, and we see that it actually also does not appear to contain a key. What did we do wrong? So key is this, key size is 6, key plus key size should therefore be that does not look right in the least, so oops, that looks better. So what we see is here that we made an assumption about how our char asterisk as array will behave, which apparently was wrong. It does not, when we add to it size, it does not increment by the amount we wanted to increment. We can test this again. We can make this to int64. Well, twice. Key plus 1. open and close one too little here. And as you see, what happens is that for some reason here the thing doesn't increment by 1, but it increments by the size of a pointer. So what we need to do here to fix the issue is to and the reason is because what we took here is kind of seen as a pointer, so we could either take a reference on 0 to get the right result, or the other thing we could do is we could just cast the value as it stands to a char asterisk, but this approach seems more reasonable. So now we remove the breakpoint and the other breakpoint and comment out our dump table, and now we expect the result to be correct. So let's see if it is. Zack, and as you see, the hash table now works properly. No, it's still buggy. Interesting. I thought I fixed that. So first thing, of course, to do is to check here if this if this behaves the way we expected it. So again, this would be buggy, and if we take this plus 1, let's see, oh, that's a bad typo. Now it should work fine. It would probably have worked without. It would probably work like this as well. Now that I think about it, C is very prone to typos breaking things, so you need to be careful. Let's rerun it because they're. Yep, suck. Now it's correct. Let's rerun it a few more times just to be sure. Yep, now we fixed the error. So it was a really very subtle bug in one place, but now it's fixed. So since we have our find function, the next thing we could do is we could add a function to remove an entry from the table, or we could try improving our hash table with more flexibility. So one thing that we could add is we could change it such that we can specify a hash function, which is a very useful addition. So first let's do that. So we'll have a function that returns int asterisk hash, and it takes obviously those arguments, and we will want to provide this as a initialization argument to our my table, which we will need to modify in the right way. So we have here a table, we map set it to 0, and its hash function will be set to, if hash is provided, then to hash, and if hash is not provided, then we will use our existing hash function. So we want to allow the user to just specify null, and in which case the system will automatically just pick our hash function. Now what we need to change, of course, is that wherever we used my hash, we will instead use the pointer in our table. And we could, of course, add much more function pointers to our table itself to handle any sort of things. For example, we could add a function to be used instead of alloc and a function to be used instead of free if we want it to use our own memory management. We could in principle provide a custom function to do the key comparison. So since we have something to calculate hashes, and we just and we might, but since we are using now our own type, we could use something more complex. So we could have something where the is equals condition is not just comparing the memory, but this is a more exotic use case, so we will not be doing this for now. Next thing we will do is we will add a function to remove an entry from our table. So that is, of course, not too difficult. one thing to note here, of course, is that there, if we want, for example, to first get the value of an entry, do something with it, and then dispose of the entry, we would kind of have to run through the whole table operations twice, although they are reasonably fast. One could think of an optimization by providing a function which would return you the value and at the same time remove the value from the table. But this would of course necessitate it creating a full copy of the data object, or our table be designed slightly differently. So for example, we could design the table such that it would always, so it would not store data in its own object, but it would require a pointer to be given to store it, and then the pointer would be just kept and then returned. So it would be a value which is easily copyable. But for now, we decided to do it this way. We could extend the table with this functionality. If we will have time, we can take a look into that. But for now, let's first add the remove function. Actually, we might want to know whether it removed successfully. So again, we can add a return value. So move from my table, small t, and it takes just table and key and size. It doesn't need anything else to operate. We will keep the dump function to be the last in our file because it's a debug function, and it's good practice to just keep those somewhere together where they are not interfering with the main code with regard to just code readability. Okay, so first thing we need to do is we need to find the right bucket. So again, we can start with this. Now we know in which bucket it might be, if it's in any. So again, here we need a loop which will check for the key, and again, if we don't find anything, we'll return an error, and if we find it and have removed it, then we could return success, or we could introduce a positive error code, 1 table entry removed, so that we indicate that the table was altered. It's a good example of a success sort of error code. So what we need to do when we have found the entries, we need to update the pointers in the right way. So let's quickly think about it. So entry, well, actually we would need to change. So first of all, let's change this to use a pointer of pointers. So that we can modify it in case we want to. And what we basically do is first we will we'll make a copy of the old element. So let's call it old equals entry. Then we will add this value. But this entry value just paste the next thing this thing would have been pointing to. So in this case, all the next. And now we just need to free the old memory. I think that should work. Let's try it out. So we had here our 10 entries, and now let's remove some of them. Suck. Oops, here. Advanced table, comma, key. We'll need a lot of keys since we will not do that in a loop. But what we can do for simplicity is we can put that in individual scope. So let's remove, actually we could use a loop and then remove every odd entry, but yeah, that's actually a nice, here we also have a change, need to provide null. It's actually a nice idea. So let's go to 5 and then just as a key take I times 2. So we remove every second entry from our table. Let's run it. Something failed. It should terminate much faster. So if we have success, then we remove. Probably there is an error with this function. So let's start here and see if the remove works properly. So we enter it. So we have a few boring things to enter first. I will put a breakpoint here that will be faster for the other entries. Then also remove this breakpoint and add one here. Okay, so we are here. So we don't hit this case, we get our hash, we get our bucket, here we get our entry, which has the data and has one next element. So let's see. Here we compare, so it wasn't this one. Oh, haha. That's of course a small oversight. We need to advance, of course, to the next element if we did not remove anything. That's one small missed thing. Next is next, and reference. I guess that was all. Let's see. Nope. We still have some error somewhere. Let's think about it. So we take the first entry. We always advance to the next. On the first glance it looks right. Let's think, let's step through it. So we have our entry. The key was not the right one. Now we go to the next one. Let's see if this is valid. It somehow is not. So let's put a breakpoint here and we run it. Let's inspect what we have broken here. So we have our entry, which needs to be dereferenced, and we get next, and we should be able to get a reference on next. Appears right. Just want to change entry, not asterisk entry. That was the mistake. Okay, let's be optimistic and hope it will run properly this time. Okay, at least we didn't crash, and the result is 1, 2 was removed, 3, 4 was removed, 5, 6 was removed, 7, 8 was removed, 9. Perfect. It works. So we already have a nicely working remove function. Let's see what else we might want to add to our table. Well, I think for simplicity we will not want to add anything more for now. It's already working nice and it fulfills the basic functionality. But maybe a few smaller tweaks which we could do is we could add the option for it to hold an element which it does not copy. So that would be quite a useful extension to the existing functions. So here, of course, we need to change how we are passing something to it. So we need to make a int asterisk data is equals new int asterisk ds equals I, and then we'll pass data here. And of course there is one more catch in this scenario, namely that if we delete an entry, it would not free everything. So our remove function would need basically to have the ability to return the data kind of the same way as find does. So we will add but then of course with the it would not be consistent with the other way of operation. So we either would need to create two, like another one which is kind of called take. I think we can make this work. We would just need to indicate somewhere which sort of behavior we want to use for the entry. So we could add, for example, a flag here which would indicate whether the value is returnable or not, and then we would always be able to return the size and the data, which is quite flexible. So let's do that. So here we'll just add a int which will contain a field, let's say data owned, and it will be 1 if the data is part of this, and it will be a 0 if it is not. And then this will dictate for us the behavior of our remove function. Okay, so we started in here. Okay, so here we can provide, we will need to provide some space for those things. Suck. Okie dokie. And now let's finish the modifications here. Where is our remove function? It's there. Good. So we start out here in our add. But then we will also need to add here a parameter which tells it whether it should own the value or not. I'm thinking if we can make this more elegant, and I think actually we could. Maybe, and then we don't even need the this thingy. This helper variable. We will reuse the data size field, and our remove function here will only have the data place for a data pointer. So the idea would be that if the data is externally owned, we will not provide a size for it. And in this case, if the size is needed, then it would be up to the user of our structure to provide means by which size can be obtained from the object itself. Okay, that sounds like a good plan. Add to table, then remove from table will not have size. Okay, and then here the idea is that size can be 0, so until here. So if size, so that's the old case, then we do the thing we always did, else past size was 0, so we need to adapt our our example here to pass 0, since we are using a reusing the pointer. We don't no longer want the table to make a copy. So if it's 0, in this case we just set, actually we don't need the brackets because we only do a one-line operation, and actually this looks nicer. We just set then data to be data. So this way our table with minimal adaptation can either hold and own the data, or it can just hold something that is owned by some external thing. And another hacky application of this mechanism actually is that it doesn't say anywhere that data actually needs to be a pointer, a valid pointer. It just means that it's a number that has the size of a pointer. So if we would have as data some numbers which fit into a pointer sized variable, we could just store it still here directly in our table without the actual need to allocate explicit memory for it, because we just abuse the data member for that. Okay, so we did this. Then we have here our find table. Here we don't need to change anything, and in remove we said we need to return data, but of course only under certain conditions. So before we free old, this we need to do anyways. We first of all check if the user wants to have data, sorry, like this, and then we check if old data size is 0, because only in this case we want to return the data, because if the data is owned by the element, then after freeing it, it would no longer be valid. And then if those both conditions are true, so we have a data and the data are not owned by our current object, then we can return data in our remove function to the caller. And then okay, dump doesn't care. Yep, that's it. We will of course need to adapt. Will we? Not even. We don't even need to adapt our table print function. It should work just fine. But what we will need to adapt will be here our delete. So you can say if remove table is equals, we'll take here the explicit value removed. So if it says removed, then we can delete data, and in no other case. Good. So that we can quickly run it to see whether we have broken something or not, but it seems to work correctly. Okay, good. So we have this, and the last thing we might be able to do within the 30 minutes we have left is we could try to quickly convert this into a C++ object. That is, I think, a nice thing to do, since it then demonstrates in a very nice way the difference between the C way and the C++ way, so to say. So let's add a class. It's see my table. The file will be only called my table. No base class. No base class. It's just as simple as it gets. Okay. And for simplicity, we will open this side by side. Oops. No, damn it. So I will make all the members protected. We will prefix them with M. And we'll need an object for our entry, which can be a struct. So let's go with struct. The object will be very similar to the one we already have created. So here we can just copy the members. We want to use the same tricks we used before, so that's a good approach. Now the class here will of course be a bit simple, since it will not have any smart pointer or anything support, but it at least would be a nice starting point for whatever we might later want to do. So of course, as said, we don't longer need this my table, because now we can use this operator. The print functions we will leave as they are. We will replace the Dingsbumster. The init function with a constructor. Will also provide a destructor. We will make it virtual just for good measure. We could also do another thing. We can define as a type for our hash function. that is a good practice when is good practice. So hash funct hash is equals null. We don't have null included anywhere, but that's not a problem for long. My table cpp to include hash std or is it, yeah, well, instructor will get something to do later. M hash is like, oops, like hash. What other members we have? Those few. So let's initialize them as well. Okie dokie. Oops, that was a copy and paste bug. That's the right destructor. So we already know the destructor will delete. Well, it will do a few things. Let's make it last. For now, let's port the functions over. All of them. Zack. The nice thing about having most of the functions prototyped here is also that we don't need to adhere to a particular order when doing things here. And one more thing, yeah, we can rename the functions later, we don't care for that. So this we can close. And we take our type. So hash calc no, init is the constructor, so this we already have. Wait, we wanted to make it differently. So this one has to go here because it's not prototyped. And this will be our initialization. Right here, better. And then get bucket stays the way it is. We will change this to take the count directly. Because otherwise the thing, it wouldn't be accessible since it would be protected. Insert entry reset is an internal function. Actually, oops. We will prototype it here as a protected function. Of course without table. And this is of course slightly different. And it needs a type. I think it was void. So we have this, that goes away. This types changes. Okay, table we don't have. Get my bucket just needs m underscore. Oops, m underscore bucket. Bucket count. And entry hash. Here we need to change the type. And there as well, table buckets does not exist. We just take m buckets. It's complaining about stoked as entry about the fact that we forgot the semicolon. So as you see, sometimes the errors, if you forget a semicolon, can be quite annoying. So let's see, this is also wrong. That needs to be this. The rest is fine. And next function, resize, that's a public one. Sorry, no, it's not a public one. It's still one of the protected internal functions. Zack. Now, since we are working with C++, not C, it is recommended to use, whenever possible, new. New this array. Yep. Bucket error -1 mem set we still need, but bucket count. Wait, why is it complaining? We have buckets. Mem set is undefined. Std. Let's add string h. There we have a mem set, I think. Yep. Okay, so here we need again to change the type, and instead of table, generally we could go with a Control F for everything and replace table with m underscore, because that's the naming difference which we did, and we don't have. Oops, wait. Yeah, that was right. That was right. That was right. Okay, so here, and we could also Control F all of those very quickly. That was wrong. Oops, that was also wrong. And then we are again at the top. So instead of 3 we need delete, and it's an array. Insert table doesn't need a table, we just go with insert, and we go here. Key size, right, we need to add the class name, of course, to our function. Let's quickly do that for all of our spare remaining functions. Okay, and the arrow start here. Oh, there's a there. So now, of course, table comma we also could remove, because that will nowhere be needed. Okay. Right here, and we have the arrows not defined. It's of course a bit unelegant, since we have two places where we define the same arrows, kind of. But we can work around this. My table here, since this one is the second to be created, we'll just say, okay, actually we need it for both. Hash if and def. So if not defined my table success, then then we define it. So normally you would not have both in your project, but since this is a demo project, we do. So what we do here to keep them apart is we check whether the name was already defined. Another option would of course be to put those things into a external file, but we want here each of those to be self-contained on its own, so that's why we do it this way. Okay, we have an arrow here somewhere. Here, get my bucket. Here actually we need the bucket count and bucket count. Actually, we could change this function to an internal one as well. Let's maybe do that in a second. Actually, let's do it now. That will help us. So here we use it, but we said we want to change that. So let's remove this, put that there, and this goes into our wrong header, into our header. Let's keep this nomenclature of putting away spaces, and here we just add a m to access it, and we are almost done, as it seems. Okay, we don't have printf, then we need stdio. I think when we have stdio we don't need the other two. No, we need but we probably don't need string. So we need, okay, then let's keep all of them in. What did I include here? stdlib. Well, but apparently it has slightly different capabilities depending on whether it's included in a C or in CPP file. And here it is now complaining that the print data takes the wrong type, because it takes char, it needs to be void. So So one thing to notice here also is that the type checking in C++ is more strict than in C. But it seems we are done. Let's compile it. One success. So let's set up a different test case. So hash if one hash else. We will kind of comment out hash everything here. Right, as we said, for data we need here void. So let's quickly in the original table here change this to be consistent. Main. Then let's quickly adapt our test case to use our new structure, which we of course also here need to include. My hash my table. So see my table. We don't provide a constructor. We can again control F all those. We can, but let's not do that because we need to make a bit of more of a change. We don't have bucket count here, so let's not add this debug feature. This comment we can change to work. Okay. Okay, and let's run it just to see whether it's working as expected. And voila, it is. So we have now implemented our own hash table, once in C and once in C++. It provides all the most basic functions that a hash table really requires. If you want any additions or more complex features, you can do that, but it's not necessary. We can slightly improve on the whole thing. Maybe not improve, but just make it different. For example, by not longer passing here hash, but instead make hash a virtual function, so that if we would want to change how hash works, we just need to derive from our table. So where's our hash function? We need to change this and that. As we don't need the would I put the type diff? Did I delete it already? Yeah, I deleted it already. Good. I think we just need here our my hash calc to be somewhere. Probably let's say somewhere here. Stack. And we will define this as a virtual. Oops. The copy didn't take. Actually, take. I just did not mark everything as a virtual function. So now we can create a derived class which will use a different hash calc. We just need here to replace the hash calcs which we have with using the function. Performance wise, it makes no difference. In both cases, we are just dereferencing a function pointer. We slightly save on code, although if we would want to do it, then we have a bit more work because we need to derive a class from this one. But I think this is fair enough. Okay, I think this will be it, since we are almost out of time, and it's also the last lecture for the semester, and technically we needed somewhere a 50 minutes break, which I always forget, so we have only 4 minutes left, so let's finish. If you have any questions, you can ask me at any time by email about your final projects. I will upload this project here to the Moodle. If you have any questions now, you can ask them. If not, then have a good weekend, have successful exams, and good luck.